Next up, I want to talk about Homework 8. Homework 8 is posted on Inkfish, and we can see it right here. So what you're going to be doing is you're going to be building a memory allocator. When I talk about building a memory allocator, what I mean is you're going to implement a thing that allows you to implement, or allows you to provide, two functions. The first function that you're going to need to provide is malloc, and the second function that you're going to need to provide is free. And for this assignment, because malloc and free, the names are taken by the C standard library, and I don't actually want to deal with replacing the C standard library, you're going to be implementing husky malloc, and so you're going to be implementing a function called hmalloc and a function called hfree. For this particular assignment, you're also going to be implementing a function called hprintstats, which will print out some stats about your memory allocator in a specific format, but that should be pretty straightforward, so I don't want to spend a ton of time on how that's going to work. But we do have this question now: how do you actually build malloc and free? And that's what I'm going to be talking about in this video. So malloc and free are the programmer's interface to dynamically allocating memory on the heap. So two functions, malloc takes size and returns a pointer to a region of memory that is large enough to store an object of that size in bytes, and then free is going to take a pointer and is going to release it back to the memory allocator so that it can be returned to the operating system or reused or something so that we don't have memory leaks. Now, a new process starts with no heap allocated. So I've drawn the picture, the address space diagram, where we have the text section and the data section at the bottom, then above that we have the heap, and then above that we have the stack. And I would say that when the program starts up, we allocate the heap, and that's not strictly true. We definitely have the stack, we definitely have the stuff that's loaded from the binary, but a new process can start up with a heap of size 0, because we don't actually need a heap, or we don't need any memory allocated for a heap until the user, the programmer, calls malloc. So when we need to get heap space, we need to allocate memory. That means we need to set up memory mappings in the process's page table. That means we need to call mmap. Now, traditionally, the system call that we used was sbreak. And we can go ahead and take a look at the sbreak system call, which still exists. The sbreak system call, we give it a size t, well, an int pointer t, but that ends up being the same as a size t. It's a 64-bit unsigned integer on AMD 64. And it's going to return a pointer to the beginning of a region of memory. And sbreak sort of is the picture that I drew. The heap is somewhere like at the bottom of memory, and it grows up towards the stack. If we're going to use mmap, there isn't actually even one heap. Every time we call mmap, we're going to get a new allocation of some region of memory. We can pick how big it is, but when we run out of that allocation of memory, we're going to call mmap again and get a new allocation of memory. So the result is that when we talk about the heap on a modern system, we're really talking about a collection of regions of memory, and we could draw the address space diagram accurately, but it doesn't really matter for the purpose of the picture. We call mmap a bunch of times when we get memory to use. Of course, if we want to allocate memory that is sort of not shared between processes and not backed by a file, we're going to have to pass the map private and map anonymous flags to mmap, which is fine. And the smallest region that we can allocate with mmap is 4K, so probably, and for efficiency reasons, we may want to allocate a chunk bigger than that. System calls are one of the relatively expensive things to do, so we want to minimize the number of system calls that we do, sort of everything else being equal. And one other thing that's relevant to keep in mind about mmap is that munmap takes an address and a size, not just an address. So if we're going to So to implement malloc, we're going to have some goals. There's no therefore here. We want it to be reasonably fast. And we don't want to waste too much memory. If we waste a little bit of memory, if we have a certain amount of overhead for memory allocations, that's okay. And speed is always a trade-off, so we have to deal with that. But we do have to be able to handle small allocations. We can't just have every malloc request turn directly into an mmap request, because if we have a loop like for I equals 1 to 100, x is sub I is malloc 10, if we allocated a page for every one of these things, suddenly instead of taking around 1,000 bytes of RAM, which is what the user's requesting, we're going to take around 400K, which is an unnecessarily larger number. So we can't just directly call mmap. And we need to be able to match the interface. And the important thing here that we're going to have to deal with is that the free function just takes a pointer as its argument. It doesn't take a pointer and a size the way munmap does. And so that means that for every allocation we do, we're going to have to remember the size. So, like minimally, if we're implementing allocations by calling mmap, we have to then be able to pass those back to munmap at some point. Now, we don't necessarily actually have to ever call munmap. It could be that the way we're implementing our memory allocator, I mean, for memory allocators in general. For the homework, there are some specific requirements on what you're supposed to do. But for a memory allocator in general, it could be that you allocate a bunch of memory, you reuse that block of memory efficiently, but you don't worry about unmapping because we're implementing part of the system. The memory allocator is part of the standard library normally. And so we know that when a process terminates, all of its virtual address space is freed, so we could make the design decision that the allocated memory is only ever actually returned to the operating system when the process terminates. And some allocators make that design decision. There's trade-offs on being able to allocate a giant amount of memory in a process and then free most of it and have the process continue running. That's not efficient if we don't free early or don't unmap early, but that's a trade-off. Now, in order to have reasonably fast performance, we'd rather reuse memory. Like when someone calls free and gives us a pointer, we'd rather keep that memory around so that we can use it to satisfy a future allocation than return it to the operating system as quickly as possible. If we did, say we want to allocate 100 chunks that are each 8K, we could do 100 mmaps. Then we could do 100 m unmaps. Or alternatively, we could do one mmap and one m unmap, and clearly doing less system calls is going to be faster. But if the allocations and deallocations are interleaved, we may also be able to avoid, if we save an 8K block, when it's freed, we can use it to immediately satisfy another allocation request for an 8K block, and that's sort of zero cost optimally, which is better than a system call, or two system calls. We do one system call to free the pages, and then another to reallocate them. So the traditional solution to this problem and what you'll be doing in Homework 8 is a free list, which works as follows. We're going to maintain a list of free blocks of memory. That list logically starts empty, but stuff will go on it eventually. We can sort of think of the free list as a cache of blocks of memory that have already been requested from the operating system that we can use to quickly satisfy requests without having to do a system call. So when memory is requested with malloc, first we check the free list, to see whether we can satisfy the request with an already allocated block. If no memory is available in the free list, we request more memory from the OS with mmap, split off a chunk to satisfy the request, the malloc, and put the rest of the chunk on the free list. And then when memory is freed, we put the block on the free list. So logically, our free list is a list and we're going to have location and size for each block. So location is the memory address, and then the size is going to be in bytes. Now that raises some complications. The first complication that we have is, where do we put this free list? So, the sort of simplest way to store a list is a variable size list, is a linked list. but that needs a memory allocator. And we're building the memory allocator, so we can't just sort of call malloc to allocate linked list cells. And the same problem for a variable length array or vector. We need a memory allocator to implement those things, and we're building the memory allocator. We don't have one. You could sort of get into building a sort of bootstrap allocator that we then use the bootstrap allocator to allocate the data structures for the memory allocator's internal implementation, which we then use to build a bigger memory allocator. And there's cases where that sort of approach actually makes sense, but we don't need to do that here. So here's sort of the key idea in a linked list style allocator. And that is, we're the memory allocator, and the thing that we're keeping track of is unused chunks of memory. And because we have unused chunks of memory that we're tracking, we can use the memory itself. The user has freed a block of memory, or we had leftover memory from allocation. We can store the data about that block of memory in that block of memory. So the two things that we need to store were the location of the memory and the size of the block. And so if we have a reference to the location of the block, so if we have a pointer to the block of memory, we already have the location, so we don't have to store the location of a block of memory in the block itself. And the other thing that we need to store is a size field about the block of memory, and we can store that in the block of memory itself as well. Now, the other complication that we have, and then we can have this be a linked list, so we're going to have a single global pointer to the head of the free list. And then each cell contains a struct, which is going to have size and then a next pointer. So that's one problem. That's how we deal with the free memory. But that leaves us another question. Where do we store the size field for allocated blocks of memory? Because every allocated block of memory is going to need to be freed. And if we are going to munmap, if it's big enough to munmap all at once, we need to track the size to be able to call munmap. But even for smaller blocks of memory, we still need the size so that we can coalesce chunks together to create a block big enough to munmap, or even just to know how to put it on the free list. We can't put something on the free list without having its size, so we need to keep track of that allocated block of memory. But again, we are the memory allocator. We can request extra bytes of memory to store stuff in. So if the user requests 100 bytes, we can allocate 100 plus size of size t equals 108 bytes. And that extra 8 bytes gives us space for the size field. So where do we put the size field? So can we put it at the end? If we have a block of memory, we have a pointer to a region of memory. I guess the sensible way to do this is always going to be drawing the chunk of memory going up. So the pointer is going to point to the lowest address in the block of memory. So if we have it like data for the user, and then size up at the top, with our like split here, then this doesn't really help us because we can't find the size field at the top of the region of memory unless we know the size already. So necessarily we need to do it the other way, where size is at the beginning of the allocation and then the data is going to be after the size. And actually, we don't want to put the pointer that we're going to return to the user to be pointing to the size field, because the size field isn't the data that the user's interested in. We're going to put our size field before the pointer that we return to the user, and then we're going to put the data, well, we're going to let the user put the data after the size field. So the size field is a sort of header, comes before user allocated block. So that's how we're going to solve that problem. So let me go ahead and try to do an example here. So let's say that we have malloc 100, malloc 100, malloc 400, free bb, dd is going to be malloc 100. Let's just see how this works out. And then of course we have free, the other stuff, but we're not that excited by that. So we're going to start off with our free list is going to point to just a null pointer. We're representing our, and then we're going to have a free list structure, struct free list cell. We're going to have a size field, and then we're going to have a struct free list cell pointer, which is going to point to the next thing. So the full size of a free list cell is 16 bytes. And that results in an important consideration here. And that is that our minimum allocation size is going to be 16 bytes if the size of a free list cell is 16 bytes. So, important thing to think about, why is that our minimum allocation size? Why can we never, if the user requests 4 bytes, why can't we just give them a region of memory that is 4 bytes big? But in any case, we're going to start off with this free list head is going to just be a null pointer. So we're going to call malloc AA. And what we're going to do is we're going to have this point, we're going to call mmap. And mmap is going to give us back let's say 16384. So we're going to have a region of memory. and 16384 is going to point to right there, and so that's where our free list head is pointing. And let's say that we're going to allocate one page just for convenience. So we're going to go ahead and say that the size of this chunk of memory is going to be 4096. And again, real-time ASCII art is a terrible thing to do, but I'm doing it because that's what's going on right now. Let's go ahead and put this in code stuff, just because it's a little bit clearer, and then I can get rid of these. All right, so we have our chunk of memory here. This is our heap. Our free list head is pointing to 16384, and then that's the region of memory. We're now trying to allocate AA, and so the way that we're going to do that is we're going to say that AA is going to be the first block of memory that we're going to pull out. So we're going to say that that's 16384 is AA, and that's going to have a size field, which is going to be 108, and then it's going to have some data here. That means that we need to figure out what 16384 plus 108 is. And now we have 16492 here. So now this has a size field of 4096 minus 108 is going to be 3988. And actually, let me go ahead and just make this a little bit clearer. So we have 100 bytes for AA here. And then at the beginning of this, we're going to have size equals 108, which means that the pointer here is actually not 16384. The AA pointer is going to be 16384 plus 8, because the value that we're returning to the user is after the size field. So 16392 is AA. Now the head of the free list is 16492, because that's the bottom of our only free region of memory. But we actually have two fields in here. So above this, we're going to have a next field, which is going to be 0. So this is a linked list. The free list head points to the first item in the linked list, and then each item in this linked list has a size field and a next field. So let's go ahead and allocate BB. So BB is going to end up being 16492 plus 8 is 500. And then we're going to split here. So we're going to have 100 bytes for BB, and again, our size is going to be 108. So 16492 plus 108 is going to be 16600. And then 3988 minus 108 gives us a new value here of 3880. Now our free list head is 16600. And we've successfully allocated AA and BB. Let's do it again for CC. So CC, again, fits in the first item on our free list here. So we're going to go ahead and take 16608 So this is going to be 400 bytes for CC. Size is going to be 408 because we still have that extra 8 bytes for the thing. So this is going to come out as 17000 minus 408. I can't do arithmetic. 3880 minus 408 is 3472. Let me get my diagram consistent. All right, and here's where we are after we've allocated CC. Next thing that we're going to do is we're going to free BB. And now it suddenly matters that we have a linked list because we need to be able to put an extra item on the linked list. So BB was 16500. That's pointing after our size pointer. So we're going to subtract 8 and get 16492. 16492 is right here. So now, rather than having space for BB, BB is now an invalid pointer. Our free list head is going to be 16492, pointing to the location where BB was because we're consing it onto the front of our free list. This is now free, so we're going to have a next field, which is 17000, since that's the next that's the next block on our free list is this 17000 up here. And now this is our state after we've freed BB. The final operation that we need to do here is malloc 100. So we're going to say DD is going to be 16500, since we need exactly 100 bytes. 100 bytes plus 8 for the size field is 108. We have 108 right here. So our free list goes back to being 17000. And this is now 100 bytes for D. So that's sort of a simple walkthrough of some stuff that could happen. Let me go ahead and do one more complication here. What if right now we allocate EE is malloc 4000? So in this case, we're going to go ahead and look on the free list. We find out that we need 4008 bytes because we need 8 bytes for our size field. We discovered that the biggest chunk on our free list is this 3472 block. So what we're going to have to do is we're going to have to actually mmap another chunk. So we're going to do the same thing that we did before. We're going to end up with size 4096. I'm going to say that this arbitrarily comes back from mmap as 32768. That's going to be our pointer value here. And then what we need to do here is sort of logically throw this on our free list. 32768. So after we stick that on our free list, then we can go ahead and try to satisfy our request for 4008. So we're going to go ahead and say that our size here is going to be 4008. This is going to be data for EE, 4000 bytes for EE specifically. Then we're going to do 32768 plus 4008. It's going to give us 36776. So now this next pointer down here becomes 36776. And EE is now 32776. I don't believe it. I think I'm off by 8. In any case, 32,768 plus 8. That's correct. Oh, right. No, it's just 4,000 bytes between the pointer and this next thing. So these numbers are correct. So here's what our free list potentially looks like once we have to mmap up a second block, assuming we're doing one page at a time. Now, we've got some complications. That's okay. All right, let's complicate this up a little bit more. What happens now if I free AA and then I free DD? So by freeing AA and DD, let's say that we want to keep the list in sorted order. That's actually something that we do want to do. We're going to do it for the sake of this diagram. We're going to end up with free list head is 16,384. Next is 16,492. Next is 17,000. And so this is a way for the free list to happen. But now what happens if we go ahead and try to malloc 200? This size is not correct. Next here is 0, and then our size was 4096 minus 4008. So our size here is actually 88. So you can see there is no free block where we can actually satisfy our request for a size 200 chunk. So what this would end up doing if we don't do something about it is it would go ahead and mmap another chunk, and we shouldn't need to mmap another chunk. The reason being, we have a region of size 216 right here, that it's two chunks of size 108 that are next to each other in memory, and we should be able to combine those two in order to satisfy this request for an allocation of size 200. So what we're going to do here for this request of size 200 is we're going to round it up to 208. Well, no. What we want to do when we went ahead and freed AA and DD, which were these two blocks, we should have noticed that they're next to each other. And then the next thing that we should have done is we should have coalesced them. So the way we coalesce them is what I just did. We delete the boundary between them, calculate the new size, and then make sure that our next pointer is pointing forward. We want to sort of join them together into one block because they're adjacent. And now when we go ahead and do this request of size 208, we can satisfy it from here. So our first thing that we would do is we'd split off 208 from the 216. That leaves a leftover block of size 8, which we would have to put back on the free list. We can't put a block of size 8 back on the free list because if we tried to, we would try to put these two fields in. The next field is 8 bytes, the size field is 8 bytes. We only have 8 bytes to put it in. It won't fit, so that doesn't work. So what we end up having to do is we're going to set our free list to be 36,776. And then we're just going to allocate FF as 16,384. So we act with the user requested a block of size, sorry, not 16,384. 16,384 plus 8 is 16,392. Right, so the user requested a block of size 200, and we added 8 because we need to store a size field. And then we rounded up to the nearest multiple of 16. Well, we rounded up to avoid having an excess multiple, avoid having to put a block onto the free list that's smaller than 16. We don't split a block into any pieces that are smaller than size 16, because 16 is the minimum size that we can fit on our free list. And so we'll end up with this allocation in the end, where this requested block of size 200 ends up being an actual block of size 216. We can do that. We're the memory allocator. We'll get back an accurate size of 216. The user only requested 200, but they got effectively 208. They just won't use the extra 8 bytes. Everything will be fine. So that is the basic idea of coalescing on a free list. Now, for the homework, for homework 8, this free list idea is the way to deal with small allocations. But what if the user says malloc 10 gigabytes? Clearly we can't allocate one 4K page and then satisfy it. Clearly we don't want to always allocate 10 gigs to be able to handle everything. And it's not necessarily useful to put 10 gigs on the free list. We want to save system calls. We don't want to be trying to do a system call for every single 4K we handle. Well, maybe for the homework we do, but we don't want to be doing it for every 100 bytes that we handle. But if the user is allocating 10 gigs and then freeing it, we probably can afford to do 2 system calls. So the implementation here is going to be in our malloc, we're just going to say if size, so size t bytes, if bytes is greater than some min size, or some maximum size, some minimum big size, we're just going to do mmap pretty directly. We're still going to add in a size field, but we're going to do mmap else. And similarly in free, if we look at that size field and it ends up being bigger than this minimum size, we can just go ahead and munmap. We'd like to unmap that so the OS can reuse it. So those are the ideas for the homework. Now, there's some design considerations that are worth looking at here. So the first question here that's worth thinking about is, should we use a singly or doubly linked list? With a singly linked list, the logic is reasonably simple for most stuff, but sometimes we're going to have to do traversals, whereas with a doubly linked list we might not. And we'll see some examples of why that might be the case, but in some of the advanced allocators we can take advantage of using a doubly linked list, especially if we include allocated memory in the list. So in the structure that I talked about here, the only thing that goes on the list is free blocks. But if we have, if we can do an insert into the list more quickly than having to do a traversal, that might be a reason to use a doubly linked list. On the other hand, doubly linked lists are more complicated to implement, and they require extra pointers, which takes up more space. Another interesting question is, should list be ordered or unordered? And if we're going to order it, ordered by what? So if we have a unordered list, we can do insertion is 01, just stick the item on the front. Unfortunately, coalescing is at least ON, maybe worse, because we have to search the entire list, and then in the worst case we have to search the entire list and then search the entire list again to find adjacent blocks of memory to coalesce. And then the coalescing process requires deleting from a singly linked list, which is tricky. So if we coalesce every time, then insertion isn't big O of 1. If we don't coalesce every time, then insertion could be quadratic in the most obnoxious case. Now if we order by size, that doesn't help us that much. We can get some optimization of having a faster big O of n, but both of the options are still big O of n. But if we order by memory location, coalescing is just about free, because as we're doing our traversal, when we find the location where we need to insert the item, the things that we potentially have to coalesce with are the item before it and the item after it. And by taking advantage of having a couple of extra local variables in the loop or recursive traversal of the list, we can do those checks without having to do a retraversal of the list, and we can actually do the insertion operation without having to do a reinsertion of the list. So asymptotically, unordered or ordered end up being about the same if we're careful with it. They're both linear time, but insertion is big O of n. But the coalescing logic is much simpler if we order by memory address. So I think this is the best idea for homework 8. Single is simpler for homework 8. So next question is, how big should the big allocation cutoff be? And we actually have an answer for homework 8, and that is that it is specified in the assignment that your cutoff is going to be 4096 bytes. That's the minimum size that it could be, since otherwise we are wasting pieces of pages by allocating an entire 4K page for an allocation smaller than 4K. But should it be 4K? Should it be 64K? 1 meg? 100 meg? I'm going to just guess and say that it's probably smaller than a gigabyte, but it sort of depends on the details. Having a big allocation cutoff saves system calls, but at the cost of putting a larger variety of different sizes onto the free list, which potentially could make coalescing a little bit trickier or less efficient. But yeah, that's a trade-off. And one more question that I want to talk about is, should we ever return memory to the OS from the free list? So we're already returning memory to the OS when we do allocations above the big size cutoff, but we will eventually get a bunch of stuff on the free list just as things happen. And if we've allocated many pages of memory and then freed many pages of memory, does it make sense to return it? And the simple answer is no, and that's okay for homework 8. And the complex answer, of course, is maybe, because that's how complex answers work. But we could say idea, if we've allocated more than, if we have more than 10 pages of 10 full pages If we have more than 10 full pages on the free list, free down to 10. Now, that gives us a problem where if we allocate, like some allocation patterns could potentially result in us sort of like allocating the 11th page and then freeing it over and over again. Although, since we have full pages, we should almost always, if we have a memory allocation request, be able to use one of these 10 pages, and we're not going to try to allocate more memory to get back up to 10. And we're only going to allocate more memory if we get down to 0. So this will let us have some pages that are available for fast allocation already on the free list, and then we return some memory to the operating system. So that might be a good idea. All right, so that's the idea of a simple memory allocator. And then there's more to talk about on how we can make it complicated, but that will be in a future video.